My name is Zhang, and I'm a postdoctoral scholar at IBM Watson Research Center based here in Yorktown Heights, New York. So far, I've been here for 2 years, after completing my PhD studies at Princeton University in late 2016. Back during my doctoral work, I was primarily focused on mid-infrared, free space optical spectrometers for environmental and medical diagnostics. However, a key limitation in those systems was size, weight, power, and cost, which we call SWaP-C limitations, and these severely constrained the market potential for these sensors, since large-scale manufacturing deployment is very challenging. When I joined IBM, this was a challenge we were seeking to address, while working with support from the Department of Energy under their ARPA-E program. I'm currently working with a fantastic team in silicon nanophotonics here at IBM, and we've managed to successfully demonstrate the first fully integrated on-chip spectrometer, which consists of a 3.5 laser, 2 photodetectors, a sealed reference cell, and a lone sensing waveguide on a single substrate. The chip itself is less than 1 square centimeter in area and uses the evanescent field of the propagating mode in the sensing waveguide to interact with the ambient gas. We have here a visual demonstration of our chip sensor so you can see they're roughly the size of a fingernail. We also expect our sensors to be very power efficient because we don't require any active thermal control for operation. The cost of these sensors is also quite cheap because much of the fabrication relies on conventional CMOS foundry capabilities for mass production. Now currently the gas inside the reference cell is methane because we're looking at utilizing our sensors in the oil and gas industry for monitoring of fugitive natural gas emissions. This is a very important application because methane, which is the primary component of natural gas, has a global warming potential over 30 times that of carbon dioxide, and the ability to deploy these miniature photonic sensors over large areas is extremely important for fast leak detection. Currently, we've already initiated a number of business collaborations with oil and gas partners, and we're looking intensively at a market transition plan over the next 24 to 36 months. We've also had a number of press releases along with our initial publications, and this project has been listed as IBM's 5 in 5, which is 5 innovations that IBM believes will change our lives in the next 5 years. On a longer scale, the vision I have for this technology is as an adaptable multi-species hardware sensing platform that can be distributed on the scale of a massive IoT network. And the data can be used in all kinds of analytics, whether pollution monitoring or health and diagnostics. So as we're progressing along with this program into the future, I'm seeing myself expanding my horizons where I keep one foot in hardware sensor development and another in the space of big data and analytics, which is an area of intensive R&D here at IBM. As a closing note, we've all seen the miniaturization of optics and electronics, ranging from your miniaturized smartphone camera to VCSEL arrays for facial recognition. So who's to say you won't have one of these chip sensors in your phone in the next 5 years? Thanks for listening.